Okay, welcome to the fourth part of this lecture on language, and now we will talk about speech perception. Okay, so let's have again a look at such a simplified diagram, which has also been called the speech chain, and we already spoke about the first half of this. So these authors say it all starts on a linguistic level, so our intention of the message we want to convey. Then it comes to the physiological level, so we have used the vocal tract to voice that message. Then we have the acoustical level, which is the actual sound waves. This is also feedback via the ear of the speaker and then goes back to the brain as well. But now we are looking at the other side, the listener or receiver of the message. And there it starts the other way around. So we have the acoustic level, the sound waves. Then we have the physiological level, the ear and how it works in the ear. You will have learned about the ear in biological psychology. And then these electrical signals in the brain are processed to the linguistic level then. Okay, so the perception of speech is actually an extremely complex and challenging task to our system, because there's such a huge variation in the way we can produce language. If you think of accents, I'm living now as a German in England, and if I hear people from Scotland, it's a little bit like a different language to me, so I often can't understand them at all. For instance, there are different speeds. Some people talk fast, others slow, pitches of the voice and everything. So those of you who may have approached this issue from a computer perspective know that this is really challenging and such a huge variety in the signal. And sometimes it's said that the word the, like in the tree, has at least 50 different ways of pronunciation. So a huge variability. Another problem which goes along with that and which makes it very difficult to understand is so-called co-articulation. What does that mean? It means that the phonemes we have spoken about before, the smallest units of sounds which bring about a change of meaning, like the example with the L and R, they are not articulated as a neat sequence, like we have one phoneme which is easy to identify, then the next phoneme which is easy to identify, then the next phoneme, but instead they overlap. So they smoothly transition into each other, which makes them much harder to identify. And a second phenomenon is that they not only just fade into each other, but they actually interact. That means the way I articulate one phoneme depends on the phonemes before and afterwards, and is slightly different and slightly modulated. As an example, think of the phoneme N in the word 10, the number 10. This is produced differently than the N in tenth, because in the latter one here, in tenth, we have the TH following the N, which makes the pronunciation, the articulation of N slightly different. To us it hears all the same, and we don't have any challenges in understanding that, but when we look at it on the acoustical level of the sound structure, we can see differences, and our brain just deals with ease with these differences. Another huge challenge, also again for computerized systems, is word segmentation. And natural speech is continuous, and there are actually no pauses between words. In our own language, we have the impression that the words are clearly separated. But if you listen to another language which you don't speak, it sounds as just one stream of words. And actually it's the same for our language. We just don't perceive it that way. Here's an example, and this is a sentence which is just normally spoken. There are no silences between words. just as a normal sentence, and this is like the acoustical recording of that. And you can pause the video now a little bit and try to segment where you think these words relate to of this sound profile. You can see here is virtually no sound, here now sound, no sound, and so forth, and to try to identify where are the word boundaries. And usually in class I give students a couple of minutes for that, but now I just say pause the video and then we'll continue. Okay, so when you do that, the answer to that is the following. And what looks like a silence and a break between words is actually here. And this is just to illustrate that there are no silences between words. And this has to be taken literal. So if we get such a signal, this gives us no clue where the boundaries between words are. But again, our brain can nicely do that. Next, I would like to demonstrate something which is called the phonemic restoration effect. And this is just a nice illustration of how our system is able to deal with noises in our acoustic input to the system. Again, I hope it will work.
Temporal induction of speech. It has been found that when a speech sound is removed from a sentence and replaced by a higher amplitude extraneous noise, such as a cough, listeners generally hear the entire sentence as intact, even when they are told in advance that a portion of speech will be missing. You will now hear an example of this phonemic restoration effect. You will be presented with a sentence in which one phoneme has been removed and replaced by a cough. The sentence will be played 4 times. Try to identify the speech sound replaced by the cough. The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city. Most listeners cannot tell that the unvoiced S sound in legislatures is missing from the sentence. Generally, all speech sounds appear to be present, and the cough does not seem to interfere with any of the speech, nor can it be located accurately within the sentence. You will now hear the sentence played with the cough replaced by silence. You should be able to locate the gap easily and determine that the S sound is missing. The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city.
Okay. So this was a demonstration. What is important here is that in the first example where the cough was present, you had the same acoustic information than in the second example. So you just first cut out, in this example, the S sound, and then you just fill it in with a cough. So we didn't hear any S, but our brain restores it. That's why it's called phonemic restoration, because it's really missing information which is there. People have done quite a lot of studies with that, and it's quite curious findings and studies results, because what has been shown is that the context actually influences which phoneme we perceive, which is covered by the cough. So there is flexibility in the interpretation, and this is just now this is now a cough sound here like this, and when we hear a sentence like the eel was on the axle, or the eel was on the shoe, or the eel was on the table, or the eel was on the orange, then this context here makes us hear either the wheel or the heel or the meal or the peel. So there's definitely some top-down processing involved as well, that we use the context to fill up the phoneme. Okay, so it's a top-down effect, as I just said. The phonemic restoration effect, so why does it exist? What is its function? And the reason for that is probably that speech rarely is a perfect signal with a perfect quality. We have a lot of external noise, and this is not only in today's day, like with traffic and everything, but also like 100,000 years ago, because actually natural sounds like animals, when you walk through the woods, crackings of branches you step on, and so there's actually a lot of noise even in nature, other human beings and so forth. So this noise may just cover certain phonemes in the language. People don't produce speech perfectly, and therefore some phonemes may not technically be missing, but maybe produced in such an inaccurate, wishy-washy way that it's hard to understand for us. And this restoration effect allows us to perceive speech, even when it has an imperfect quality, effortlessly. And so it's an automatic process, and we don't need any effort and think, oh, there was something covered, what was it? If you think back about the attention lecture. So we don't even notice that our brain automatically fills it up, and so we can understand language more easily. If you have any questions, post them on the BBL board or bring them to the seminar.